There are ordinary differential equations of first order and higher degree, which are not actually Clairaut's equation, but by suitable transformation, we can reduce them to Clairaut's equations. So in this video, we are going to discuss those kind of first order and higher degree ordinary differential equations. Now, unfortunately, there are not set rules using which we can easily recognize, okay, this is the equation and this is the kind of transformation which we can use to reduce it into Clairaut's equation. But still, there are a couple of forms which are recognizable, and in those forms, we know what the substitution we have to use to reduce the equation to a Clairaut's equation. Now, first form is suppose there is a first order and higher degree ordinary differential equation of the form y square is equals to p xy plus some function of p variable and y over x variable. Suppose there is a ordinary differential equation of first order higher degree which is given in this form, or we can convert that equation into this form. Of course, p stands for dy by dx, right? In that case, the transformation we will use is u equals to x square and v equals to y square, right? Using these transformations, this equation will convert it into, in this form, v equal to pu plus some function of capital P, right? Where u is dependent variable, u is independent variable, v is dependent variable, and P stands for dv over du. And this is clearly Clairaut's form, and we can write its solution by simply replacing P by arbitrary constant C, right? Another form is suppose there is a first order and higher degree ordinary differential equation, okay, which involves functions like e raised to the power mx and e raised to the power nx. In that case, I beg your pardon, and e raised to the power ny. In that case, the transformation we use to convert that higher degree equation into Clairaut's form is u equals to e raised to the power l x, and v equal to e raised to the power again ly. What is l? L is equals to greatest common divisor of m and n. Let us take a few examples to understand how to convert or reduce a given higher degree equation to Clairaut's equation. So our example one is we have to solve this equation, and the equation is example we have to solve this equation x square multiplied by factor y minus px equals to y p square, where p is equals to dy over dx. Well, how do we come to know that we can reduce these equations to Clairaut's equation? Because of the factor y minus px. So this gives us an idea that it can be reduced to a Clairaut's form, right? We can use transformation u equal to x square and v equal to y square to solve this problem. And this is possible because we can convert this equation into this given form, y square equal to pxy plus a function of p and y by x variables. So let us rewrite this function. Let us name the given equation as it is given as equation number one. Now we are rewriting it. We can rewrite it as so we are solving it. We can rewrite it as y minus px equals to y p square over x square. We have divided throughout by x square, right? And now we need y square, so I'm multiplying this equation by y. So this become y square minus pxy is equals to p square y square over x square, right? And this can be written as p square equals to y square equal to pxy plus p square y square over x square. So we can see that the given equation we can rewrite it as in the form y square equal to pxy plus some function of p variable and y over x variable. So this allows us to take the transformation as u equals to x square and v equal to y square. After that, it will be converted into Clairaut's form. So this was just a demonstration that yeah, we can take u equal to x square, v equal to y square transformation. Okay, so going back to our original equation, okay, we substitute or transformation is let u equal to x square and v equal to y square. It means the dependent variable y will be converted into new dependent variable v and the dependent variable x will be converted into a new independent variable u, right? So our b stands for dy over dx, which we can write as dy over dv multiplied by dv by du multiplied by du over dx, just using repeatedly using the chain rule, right? Now dv by du, we have new set of variables. In place of dv by du, we are denoting it by capital letter P. U already we du by dx, we already know u in terms of x square, so u equals to x square. It means du over dx equals to 2x, right? So in place of du by dx, we can write 2x. Okay, again we have v equal to y square, so we have v equal to y square, dv over dy equals to 2y. By reciprocal rule, dy over dv is equals to 1 over 2y, right? So dy over dv is 1 over 2y and du by dx we already written 2x. So we have p is equals to and 2 cancels out. So small p, which represents dy by dx, we can replace it by px over y, where P stands for dV over du. Now we substitute all these values into equation number 1, right? Here we replace it by u, x square equals to u. Y, as of now, we take it, we let it be y and minus. In place of small p, we will write capital P x over y is multiplied by x. This is equals to y. In place of small p, we will write capital P x over y. So capital P x over y whole square. Now this one is u. Let us take LCM here. Y multiplied here. This becomes y square minus capital P into x square whole over y. This one is equals to y p square. X square will become x square, we will write it as u. Y square, we will write it as v. We cross multiply using y, so this becomes u. Y square is v minus p x square is u. This one is equals to y multiplied by y becomes y square. Y square will be replaced by v. This is p square u over v. V and V cancels out, and after that U factor will be cancelled out with U. So we have V minus PU equals to P square, and this one is V equals to capital PU plus P square, which is clearly Clairaut's equation with a dependent variable as B and independent variable as U. Capital P stands for dV over du. So Solving this Clairaut's equation, the general solution for V will be V equals to, we will replace the P variable by arbitrary constant C U plus C square. This one is general solution, right? But our original equation had the variables X and Y. UV came into picture because of this transformation equation. So writing back V equal to Y square and U equal to X square, the general solution of the original equation, the general solution of the original equation will be, V will be replaced by Y square. This is equal to C X square plus C square. So this is the general solution of the given equation, which was not a Clairaut's equation, but we converted it into Clairaut's form using these transformations. Let us take one more example, and in this example, we have to solve this equation. The equation is px minus y multiplied by another factor is x plus py. This one is equals to 2p. Now let us give it name equation number 1, right? Now we have p into pp square, so this is a higher degree ordinary differential equation. Of course, p stands for dy over dx, derivative of y with respect to x. Now these factors px minus y, x plus py, these factors involved in a Clairaut's equation. So this gives us an idea. Okay, this one is not Clairaut's equation, but we can use suitable transformation to reduce it into Clairaut's form. Now, we are not doing it here, but if we rewrite it, we can see that we can convert it into this form, y square equal to p multiplied by xy plus some function of p and y by x, right? So straight away, we are taking these transformations. So we let u equal to x square, v equal to y square. And as we did in example 1, P, that is dy by dx, will reduces to capital P x over y, where capital P stands for dv over du. Now let us put all these values into equation number 1, right? So in place of P, small p, we are writing P x over y multiplied by x. P is replaced by px over y. P is capital Y, stands for dv by du, minus y multiplied by x plus p. Again, small p will be replaced by capital P x over y. And this one is multiplied by y. So multiplied by y equals to 2. Small p will be again replaced by capital P x over y. And let us simplify it, right? So taking LCM here, the first factor becomes capital P x square minus y square whole divided by y. Again, in this case, y will be cancelled out with y. And x we can take out common out of this factor. So this is x comes outside, this becomes 1 plus p. This is equals to 2px over y, right? Now, x factor and x factor will cancel out. Y factor and y factor will cancel out. P x square will be replaced by u variable minus y square will be replaced by v variable. This is 1 plus p equals to 2p. Let us rewrite it. This becomes pu minus v equals to 2p over 1 plus p. Okay, again rearrange these terms. P we take right hand side, p will become positive. 2p over 1 plus p we take left hand side, it will become negative. So we rewriting it, it becomes pu minus 2p over 1 plus p equals to v. And we can rewrite it as v equals to pu minus 2p over 1 plus p. So clearly this one is Clairaut's form, right? And solution, general solution in this case of this differential equation with the dependent variable as v and independent variable as u will be v equal to p will be replaced by arbitrary constant c. U remain as it is minus 2c over 1 plus c, right? Now our original equation was given in x variable and y variable, so writing back in place of u x square in place of v y square, our final solution will be v will is y square. This is equal to c remains as it is. In place of u we will write x square minus 2c over 1 plus c. So this one is general solution of the original given equation, which was not Clairaut's equation, but using the suitable transformation we converted it into Clairaut's form, and because of that we could find the general solution of the original equation. Now let's take one more example. This is our example number 3, and this example involves exponential functions. So we have to solve this equation, and this is e raised to the power 4x p minus 1 plus e raised to the power 2y p square is equals to 0. Now first thing is that how come we are considering it to be an equation which can be reduced to Clairaut's form. Okay, please. P square means is higher degree first order ordinary differential equation. So first thing, it will be difficult to solve this equation into linear factors of p variable, right? Again, it is difficult to solve this problem for y variable, similarly for x variable. Okay, so the only thing that is left is either it is Clairaut's equation or it could be reduced into Clairaut's form. Clearly, this is not a Clairaut's equation. That's why we will opt for some suitable transformations using which we will convert it into Clairaut's equation. And we already know that if uh, higher degree first order ordinary differential equation involve exponential function in terms of x variable and y variable, so our substitution is like this one, right? So in this case, now in this problem, GCD greatest common divisor of coefficient of x is 4 and coefficient y is 2. This one is 2. So our substitution will be, we will take u as, let u equals to e raised to the power 2x and v as e raised to the power 2y, right? Okay, let us see what will be our dy by dx, which we are denoting by small p. Again, writing this p as dy by dx as dy over dv multiplied by dv over du multiplied by, this is v, du over dx, right? dv by du, we will write it as capital P, right? We have u equals to e raised to the power 2x. So we can write du over dx equal to e raised to the power 2x multiplied by 2. E raised to power 2x is u, so we can replace it by u. So this will be u. Again, v is e raised to the power 2y. So dv over dy equals to e2 raised to the power 2y. This is 2 e raised to the power 2y. We have assumed as v. And by reciprocal rule, dy over dv equals to 1 over 2v, right? So in place of du by du over dx, we will write 2u. So this is 2u. dy over dv is 1 over 2v. So this is 1 over 2v. 2 and 2 cancels out. So our small p is equals to capital P U over V, where capital P stands for dV over du. So our transformation equations are u equals to e raised power 2x, v equal to e raised power 2y, and because of that we got small p is equal to capital P u over v, where capital P stands for dv over du. So given equation, so let us put this in say this equation we are giving name 1. we put it there. So e raised to the power 4x, e raised to the power 4x, we can write it as e raised to the power 2x whole square. In place of p, we will write capital P u over v minus 1 plus e raised to the power 2y is v p square, this is small p, so this will be capital P u over v whole square, this is equals to 0. Further simplifying it, e raised to the power 2x, we can replace it by u, so this becomes u square, right? So this one is, let us take LCM here, so we, this factor becomes pu minus v whole over v, this one is plus v pu over b whole squared, so this will become p squared u squared over v squared, this one is equals to 0, right? So here v and this one is v squared, so this v cancels out and the numerator denominator here remains v, fine. So we are now multiplying this entire equation using a factor v over u square, right? So multiplying this entire equation by v over u square. So we will get u square will cancel out, v will cancel out, again here u square will cancel out, v will cancel out, and we will get pu minus v plus p square equals to 0. Now rewriting this equation, let us bring this v on right hand side. So we get pu plus p square equal to v. Rewrite this equation as v equals to pu plus p square, which is clearly Clairaut's equation with the u as independent variable and v as dependent variable, and its solution, its general solution simply will be v equals to, will replace p by arbitrary constant c, v equals to cu plus c square, right? And now our original equation was given in x and y variable, so let us write e raised to the 2 e raised to the power 2y in place of v and e raised to the power 2x in place of u. So this general solution before in xy variable form becomes e raised to the power 2y is equal to c e raised to the power 2x plus c square. So this one is the general solution of the given higher degree differential equation, which was not a Clairaut's equation but by suitable transformation equation, we reduce it into Clairaut's form. Now, we solved three examples using the known forms, in which cases we knew the type of transformation equations we have to use. But in general, there is no set rule to find these transformation equations. It depends upon the individual problem. More problems we practice to solve, the better we will have an idea what kind of transformation we have to take in a particular problem. As of now, in this video, we solved three examples in which we already knew that these types, which are of type 1 and type 2, and where we knew that the kind of transformation we have to use. Thank you.